pivotal key to understanding tensors is to have a good grasp of vectors and dual vectors. Once you have these down, tensors are really just a straightforward generalization of them. In this video, I will guide you through a two-step process where we will first review what vectors and dual vectors actually are, and then we'll see how this generalization occurs. By the end of the video, you will understand exactly what a tensor is. Okay, so first, let's discuss vectors. What really is a vector? The common notions of a vector as an ordered list of numbers or as an arrow in space are just two specific instances of the much broader and abstract mathematical concept of a vector. According to the subject of linear algebra, a vector is really just an element that lives in a larger abstract space known as a vector space. And a vector space, which is usually denoted by a capital V, is a set that satisfies these basic axioms. The first four axioms show how vectors can be added together, and the final four axioms show how these vectors interact with scalars, which are elements of another algebraic structure called a field. Okay, so vectors are things that live in vector spaces. But what about dual vectors? What exactly are they? In order to understand what dual vectors are, we need to introduce something called a linear functional. A linear functional is a map that takes in one vector and maps it to an element in the underlying field. And when it does this, it must satisfy the two properties of being linear. In principle, this could be a map to any field, but for the purposes of studying tensors, it helps to focus on the case when the underlying field is the set of real numbers. Now, these could be maps of any kind as long as they are linear. A couple examples would be the mean map, which sends all vectors to their mean value, or the zero map, which sends all vectors to the number 0. Now, dual vectors are just these linear functionals, and the collection of all of the linear functionals that can be defined for a specific vector space actually forms itself another vector space, one that is called the dual space. So, dual vectors or linear functionals are elements that live in the dual vector space, and this will hold for all vector spaces. So for any vector space V you can think of, there will always be an associated dual space V star that you can define by taking all of the linear functionals on V. And an alternative way to refer to these spaces that you might have seen is that the elements that live in the vector space are contravariant vectors, while the elements that live in the dual space are covariant vectors. Okay, so now we are finally ready to tackle the definition of a tensor. A tensor T of type KL is a multilinear map from K dual vectors and L vectors to the real numbers. Now, I know this definition can seem like a headache, but if we break it down piece by piece, it will become crystal clear. The first thing I'll address is this notion of type. Another word you might encounter for it is rank. It simply captures how many elements you are taking as inputs from each of the above spaces, where the first K elements are from the dual space and the next L elements are from the vector space. And this X symbol between them all is the Cartesian product. Secondly, this map must be multilinear, which basically just means that it is linear in each of its arguments. The best way to understand this is to go through an example. So let's consider a type 1-1 tensor. This means that as inputs, we take one element from the dual space, let's call it phi, and one element from the vector space, which we'll call v. And to see how multilinearity works, let's suppose that phi can be written as a linear combination of two dual vectors f and g. And the vector v can be written as a linear combination of vectors v1 and v2, where all the scalars are coming from the real numbers. So this will turn the input into this expression. And then each argument will need to be linear. So if we go through them one by one, then we arrive at this equality. And remember, a tensor is a map to the real numbers. So this whole thing must be a real number. And the same thing goes for each of these expressions. So that is a type 1-1 tensor. Now, to really let the definition of a tensor sink in, we will go through a couple simpler examples that show how tensors generalize dual vectors and vectors. First, let's consider a type 0-1 tensor. This takes one vector as an input and maps it linearly to a real number. But that's exactly what the definition of a dual vector is. So a dual vector can be viewed as a tensor of type 0-1. Now what about a type 1-0 tensor? This takes one dual vector as an input and maps it linearly to a real number. This is actually just a vector. And the reason is that once you construct a dual space, if you then ask, what are all the linear functionals that you can define on the dual space? So what is the dual space of the dual space? It turns out that you end up back at the original vector space. Thus, the dual space of V star is just V. And finally, how about a 0, 0 tensor? This can be viewed as a real number or equivalently as a map from a real number to another real number. So it's just a scalar. Okay, I think that's a good place to stop for this video. Be sure to stay tuned for future videos in this playlist where I will go over almost everything you need to know about tensors in physics. I plan to cover tensor products, Einstein summation notation, and much more.